Hi guys, Audrey here. So today we're going to learn a rule for calculating limits that involves derivatives, so really major throwback here, that's called L'Hopital's rule. So in order to kind of set up L'Hopital's rule, we need to remember a few things that are important that we learned in Cal 1. So the first thing is indeterminate forms. So in Cal 1, when you were evaluating limits, you learned two major indeterminate forms. The first of which is 0 over 0, and the second of which is infinity over infinity. And what these things did is they told you that you needed to do something else in order to evaluate the limit. Seeing 0 over 0 or infinity over infinity actually meant that there was like a number hiding behind there. So in other words, 0 over 0 could equal to 0, it could equal to infinity, or it could be going to infinity, or it could also be like 5. The same thing with infinity over infinity. So it's a number that's hiding some other value, or rather a form that is hiding some value. Some value. So it could result in 0, positive and negative infinity, or any other number. And so the reason that 0 over 0 and infinity are indeterminate forms, or rather, we're just going to try to understand really quickly why they're indeterminate forms. 0 over 0 is an indeterminate form because if you look at the top there, that 0 on the top is like multiplication by 0. And we know that multiplication by 0 always gives 0. Multiplication by 0 results in 0. Division by 0, though, if you go back and remember, we know that division by 0 is not allowed, but division by 0 results in infinity. It could give you infinity, it could give you negative infinity, or it could be like doing two different things on the left and right and does not exist. But regardless, there's a vertical asymptote there. Division by 0 means infinity. So division by 0 results in plus or minus infinity. And so what this tells me is it's like the top is fighting for this thing to be 0 and the bottom is fighting for this thing to be infinity. And so it's kind of like a battle between the zeros. Which one will come out on top? Maybe it will be 0. Maybe the 0 on the bottom will be stronger and it will be infinity. Maybe they'll kind of cancel each other out and we'll end up with like 84. So the same thing is happening with infinity. Multiplication by infinity just makes things bigger. If I'm like 5 times infinity, well, that's just like 5 times bigger than infinity, which is just a bigger infinity. So 5 times infinity would just be infinity. Multiplication by infinity results in infinity. Division by infinity results in 0. So maybe you don't remember this, but it is something that you learned back in Cal 1. If we get division by infinity, a constant over infinity, that gives us a 0. The bottom is getting really, really, really big while the top stays constant. Well, then that means the number gets smaller and smaller and smaller and is on its way to 0. So what these things mean, so what this means here is that the infinity on top is fighting for this thing to be infinity. The infinity on the bottom is fighting for the thing to be 0. So it's like a battle between the infinities. If the infinity on top is stronger, we'll get infinity. If the infinity on the bottom is stronger, we'll get 0. Or they could kind of balance each other out and we'll end up with like 5. So the actual value could be anything. And so to find that value, you've learned a few methods to do that. You learned how to factor and cancel out. You learned how to clear denominators. You learned how to rationalize. You learned how to take the big terms when we're dealing with infinity over infinity. So this semester, we're going to learn L'Hopital's rule, which gives me another way of dealing with these two indeterminate forms. So that said, the first thing is we're going to remind ourselves of two of the things I just talked about up there. The first is that the limit as x approaches infinity of some constant over x that results in a constant over infinity, which is just equal to 0. This is something that you need to know. Now, a caveat to this is that even if that x is up top with a negative exponent, so this is the same thing as the limit as x goes to infinity of cx to the negative 1. So that negative exponent also means infinity to the negative 1, the result is 0. So infinity with a negative exponent up here results in 0. Then we also talked about up there how division by 0, so if I have x goes to 0 of a constant over x, it could result in infinity, it could result in negative infinity, or it could result in does not exist. And these two limits right here are things that you should know. You should be comfortable with them. So get to memorizing if that's not already in your head. All right, so now how is all of this useful to us? How are we going to deal with this in a different way than what we did last semester? And the answer is L'Hopital's rule. And L'Hopital's rule is using derivatives to calculate limits. The rule itself says, L'Hopital's rule tells me that if plugging in results in one of those two indeterminate forms we just talked about, 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x, so in other words, we got that infinity on the top and then the infinity on the bottom, or that 0 on the top and 0 on the bottom, so we have a ratio of functions. So L'Hopital's rule tells me that that equals to the limit as x approaches a of f prime of x over g prime of x. In other words, the limit of a ratio of functions is equal to the limit of the ratio of the derivative of those functions. The limit of the ratio of functions is equal to the limit of the ratio of derivatives. So in other words, I can just do the derivative of the top over the derivative of the bottom. And so, as you can tell, we're gonna need to remember our derivative rules in order to do this. So this is L'Hopital's rule. Let's see it in action. Let's see how it will work out if we actually do problems. So, examples. Evaluate the following limits. And we're going to start off with a simple one. So the simple thing will be the limit as x approaches 0 of sine x over x. So the first thing that we need to do if we want to apply L'Hopital's rule is plug in. And that's really the first thing that you should do anytime you see a limit ever, is to plug in. And when I plug in here, I get sine 0 over 0, which is 0 over 0. So that is one of the two indeterminate forms that allows me to use L'Hopital's rule. So that's good, we got it, which means that we're allowed to apply L'Hopital's rule. Now for that sine 0, you do have that table in your notes of trig values so that you should know, and this is one of them, but you also have your calculators and you can just plug in sine 0. When you're doing that though, it's important to remember to keep your calculator in radians. So just press the DRG button, make sure it says rad up top. So this limit as x goes to 0 of sine x over x, I got that 0 over 0, which means I am allowed to use L'Hopital's rule. So when I'm using L'Hopital's rule, I'm going to write HR up on top of the equal sign. And that's important because it tells me that you're using L'Hopital's rule and that you need to be telling me that. So that makes it easy for me to follow your work to see, oh yeah, you're applying L'Hopital's rule. So this is to indicate that you are applying L'Hopital's rule. And so here we'll get the limit. As x approaches 0, the derivative of sine is cosine. So I do the derivative of the top divided by the derivative of x is 1. Notice I did not do a quotient rule here. I did the derivative of the top and then the derivative of the bottom. So I got cosine x over x, and then I plug in again, and this gives me cosine of 0 over 1. Well, cosine of 0, again, this is from that table that you guys have, but also you can plug into your calculator, make sure it's in radians. Cosine of 0 is equal to 1, so this is 1 over 1, and the answer is just 1. So here we applied L'Hopital's rule. And what did we do? First we plugged in. So first plug in and see if you get 0 over 0 or infinity over infinity. First plug in. If you get 0 over 0 or infinity over infinity, apply L'Hopital's rule, which we're going to be writing as HR from now on. So apply the rule. And then plug in again. So plug in again. So in that second step, again, like I said, I want you to remember to write HR on top of the equal sign. To indicate you are using HR. Okay, so next example. We're going to keep going with a simple one, but this one's going to give us some things that we need to know about natural log. So the limit as x goes to 1 here of natural log of x over x minus 1. So the first thing that we do is we plug in. And when I plug in, I'm going to get ln of 1 over 1 minus 1. So ln of 1 is a value that you can put into your calculator, but it's also a value that shows up quite a bit when you're doing L'Hopital's rule. So it's useful to know that it actually just equals to 0. So that's 0 over 0, which means that I am allowed to apply L'Hopital's rule here. So we'll have equals, we'll have our HR on top of the equal sign. The limit as x approaches 1, we do need to know the derivative of ln x. It is 1 over x, and you know that because the antiderivative of 1 over x is ln x. So remember, they just kind of go back and forth. The antiderivative of 1 over x is ln, so the derivative of ln is 1 over x, and then the derivative of x minus 1 is just 1. So now I can plug in again, and when I plug in again, I get 1 over 1, which just gives me 1. So the answer here is 1. Now, this will also be, I'll keep this in B. I'm going to use the exact same function, that ln x over x, but instead of having the limit approach 1, I'm going to have the limit approach infinity. So the limit as x approaches infinity of ln x over x minus 1. So when I plug in here, it's kind of like I have a ln of infinity over infinity minus 1, which gives me infinity over infinity. So if ln of infinity going to infinity is not something you know, it is something that you should know. In a second, I'm going to look at a graph of ln, and having the graph of ln in your head is actually incredibly helpful when we're doing these ln problems. That said, there are a few limits that you just need to be comfortable with, and we're going to look at those as soon as we finish this problem. So ln as x goes to infinity is actually just going up to infinity. We'll see that in a graph in a second. So the fact that I got that infinity over infinity, that is one of the forms that allows me to use L'Hopital's rule. So here I'll have HR, the limit as x approaches infinity. We have the same derivative, so I do the derivative of the top over the derivative of the bottom. So again, I'm just applying L'Hopital's rule, not a quotient rule, derivative of top over derivative of bottom. And then when I plug in, I end up with 1 over infinity, which, do you guys remember what that is something that we reminded ourselves of when we started class today. 0. The limit as x goes to infinity of a constant over infinity, or of x, is just 0. So the answer here is 0. All right, so there are a few things that you guys need to know about natural log. So we're going to take a look now of the natural log function. So here, this is to know. And if I have my graph here, natural log looks something like this, ln x. So actually, I'm not going to write that on the y-axis. I'll write it over this to the side here. So this is like f of x is equal to ln x. So in Cal 1, you guys learned how to read limits from a graph. So let's look at a few limits that we need to know here. We just saw the limit as x approaches 1 of ln x. So this right here is 1. And we can see that the value there is just 0. So the limit as x approaches 1 of ln x is just equal to 0. The limit as x approaches infinity of ln x, well, here we can see if I follow the graph up, as my x values get bigger, so this is like x on the way to infinity, my y values are just getting bigger and bigger and bigger forever. So the limit as x goes to infinity of ln x is just infinity. Now the limit as x approaches 0 from the right, well, that would be here, my x value is going to 0 on the right side. So I'm on the right side of 0. What's happening to my y values as I let x get closer and closer to 0? Well, if we follow that graph down, what's going on with our y values? We can see that those y values are getting smaller and smaller and smaller forever. So the limit as x approaches 0 from the right of ln x goes to negative infinity. But what if I were to ask you for the limit as x approaches 0 from the left of ln x? So that would mean go to the left side of 0. So here I'm approaching 0 from the left, but notice there's no graph here. Ln is only defined for positive x values. Thus, when we do the antiderivative of 1 over x, we have ln of the absolute value of x. We need it to cover all values, but it's not defined at negative values. So here, the answer to this would just be does not exist, and this is because there's no function there. And in the same way, there's no function there. I can't ask you for the limit as x goes to negative infinity of ln x because there's nothing over there. Like, where would I look? I would look at nothing. There's nothing to look at. So I'm not going to ask you for negative infinity because that doesn't make sense. It's just not defined there. Okay, so this is just some things that you need to know about ln x. There you go. Okay, we're just going to do one more problem real quick involving trig. And so we already saw sine x over x, and that was pretty straightforward. Unfortunately, sometimes with trig, things get extra super complicated. So we're going to do one more problem with trig. I'm going to do it in another video, though, so that we can keep this a little bit separate. So for this video, that's all. Bye, guys.